Now let's talk about alkenes because I know you love reactions. Please remember that these videos are 100% focused on DAT. So now let's start. In this occasion, I want to touch base with alkene reactions and give you the key points that you need to know to master this topic. They're very genetic and very predictable if you know the exceptions and you separate between which one are Markovnikov and which are anti-Markovnikov. Most of them are Markovnikov, and they have three exceptions, that is to do methyl shifts and hydroshift. So let's start with hydrogenation, catalytic reduction. You're going to see the reaction. Let's start with this alkene, and we're gonna react it with this hydrogen. This hydrogen will be in a solution with platinum. Platinum has proven to be the standard catalyst for many oxidation and reduction reactions in both acidic and basic electrolytes. It will be an ideal candidate for the process of fusible studies. You're going to see this, and as soon as you're going to realize that it's a catalytic reduction, and this simply going to do a syn addition of this hydrogen. So I'm going to make a note about that this is a syn addition. Now let's continue with hydrogenation, and we're going to create two reactions. One is with halide, which is we're gonna name it HX, and CCl4. Please notice that our X, let me put it in another color, our X is equals to, it can be any halogen like Cl, Br, or iodine. So let me add it here with another color so you can separate it. But also we're going to react this hydrogen or halide, in this case HBr. We're going to react it with ROOR, which is equals to what? Equals to peroxide. The product of our first one, which is a halide with the CCl4, it will be simply a Markovnikov addition, but since you have a better position, which is a tertiary position, you're going, instead of adding here, you're going to shift it and do a methyl shift to this position. This will create a carbocation intermediate. Let me show it here. And it's good for you that you notice that everything that goes to the most stable position will have a carbocation intermediate. But in this case, if you notice here, this will go to the least stable position because it has peroxide. Peroxide will make only not two HCl hydrochloride, but HBr, peroxide will push HBr to the least stable position. So instead of going to this position, it will go to the least stable, which is here. So what it's going to do? It's going to create a radical intermediate. And it will go to this position to make this product. In this case, it will go and make this product. So what if I have, instead of a hydro meaning hydrogen, I only have a halogenation. Let me put it here, halogenation. In this case, I will have a double addition, because remember that these are diatomic, so they cannot be alone. So let's add it here. Let's add my reactant and reagents. Remember that X represent chloride, bromine, and iodine. So in this product, I am going to have the following. I am gonna have a anti-addition of my X, and I'm gonna write here anti-addition. And as a reminder, my X is Cl or Br. This one in this case is mark, hydride shift. You add a carbon or a methyl shift. And also my X equals to Cl, Br, and I. ROOR equals peroxide. And this one in this case is anti-mark. As you already observed the pattern, you can see the alkenes are very standard. You always, or most of the time, going to break the double bond. Now let's react this alkene with a halogen. In this case, we're gonna represent our halogen with an X. Halogens are diatomic, so you're gonna add 2 halogens, and we're gonna react it in water. So this is halohydrine. Hydrine, you're hydrating. So if you're hydrating, you're adding water to any alkene or any reaction, actually, you're going to add what? You're going to add OH. Can I explain before? You're going to break the double bond. You're going to add OH to the most stable position and add 1 halogen, either chloride or bromine, to your least stable position. As a side note, if you are reacting this, so instead of having water, you have an alcohol. If ROH, then your product, it will be an ether. For acid catalyzed hydration, let's put any strong acid. H2SO4 is the most common that you're going to see. You know what, let me draw it backwards, because you also might be able to see it in this way. H2SO4 and H2O. This is able to go to the most stable position and it will add OH. This is one of the exceptions that go Markovnikov and also add or go and do a methyl shift. So you're going to add OH, and of course your hydrogens are going to be seen. Please note that with ROH or an alcohol, if you have an alcohol here in water, you're going to produce an ether. Also, you can see this reaction in the form of hydrogen in water or an acid in water. Remember that this H3O is a strong acid in water. As I mentioned before, most of the reactions for alkene are Markovnikov. So for this one in particular, you're going to add OH. This is one of the reactions for alkene that add OH. Notice here your water. So you're going to break your bond, and you're going to add your water to the most stable position. Please notice that you don't do any shift. For oxidative cleavage, please know that this one is in hot. You have permanganate in hot, notice here. So what you're gonna do is you're going to break this alkene bond in half. So you're gonna use the first half that is going to contain the entire carbon bond. You're gonna use your half, this is your first half, and you're going to add oxygen. Here, of course, you have a hydrogen. But since you have it in hot, instead of adding just hydrogen, you will add OH. What you're going to do with the other half is the same thing. You will add oxygen, add OH, and of course you will have a hydrogen attached to the carbon. Acosta Mercuration is the same thing as oxymercuration. The only difference is what you are adding. Please notice that you have H2O here, and in this case you have an alcohol. So that's the difference. You're adding a OH to one end, or you are adding oxygen with a carbon chain to the other end. So let's present it here. Here you're going to add OR, R being your carbon chain attached to your oxygen, and that's it, you will be done. For epoxide formation, you're going to eliminate again your double bond, and you're going to replace it with your epoxide. For this case, please know that you can also see this region as MCPBA. For dehydrolyzation, these both are seen. This is anti. Please notice with what you are reacting. You have permanganate in cold. In this case, you have it in hot. It's different. So when you have it in cold, it's a different product. And notice the MCPBA or peroxide is reacting with the strong acid in water of or H3O. In this case, it's alone. In all the cases, you will add OH. The only thing that changes is the addition, if it's a syn addition or a anti-addition. Hydrogenation oxidation is also adding OH. Let me add it right here. In this little corner, you add OH. But this is one of the regions that OH, that it will be anti or anti-Markovnikov. So you will add it in this position, that your OH, this is, let me write it here, anti-Mark. And last, we have Osonolysis and Cyclopropanation. They both have two different routes. So let's start with Osonolysis. For the first time, you will cut again your double bond in half and create two products. The first one, you're going to add oxygen, and you're simply going to leave a hydrogen and replace it, and the other half you will complete with a oxygen. You only add oxygen. You cut in half, you cut your double bond in half, and you add your oxygen. You leave it just like that, and that's your product. There is no memorization in this, as long as you know that what you need to add is simply a oxygen. That's it. For the second one, let me add it in another color. you will do the same. You will cut it. But what is different is what you're going to add, because remember that you have here peroxide. This is H2O2. Also peroxide, you will see it as ROOR. So you will add an oxygen, of course, but also you will add OH. Your second product will be what? You have your same thing, but you will add OH. This is called carboxylic acid. For cyclopropanation, please note that zinc is a catalyst. So zinc will cut this double bond and just make alkene. So that's what it's doing. So this is also called a Simon, let me put it right here, Simons-Smith reaction. And what this is going to do is to do this triangle. That's it. You are done with this reaction. You don't have to do anything else. Now for this one, in this case, it could be a halide. So what we're going to do is to do the same triangle, but we're going to add our halide double, okay? Double addition of this halide. Let me write it down here. So this is the end of our review for alkenes. I'm gonna try to record another video for alkyne. Please ask me any question in the study group. Have a good day.